Good day, learners. Welcome to our physical sciences lesson. My name is Aminim Kize. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Grade 11s, our focus is still on acids and bases. Even last term, we were focusing on that. But remember, there are so many subtopics, under acids and bases. So our focus today, when it comes to our exam guide, we are going to focus on acid-base titrations, looking at specific indicators for titration, choosing from methyl orange, phenolphthalein, and bromothiamyl blue, defining the equivalence point, the end point, also perform stoichiometric calculations based on titration of strong and weak base, a strong acid with a weak base, a weak acid with a strong base, and also calculations may include the percentage purity. And we are also going to look at the apparatus that we need to perform titration, a standard solution, describing the safety precautions, describing the measures that need to be in place to ensure reliable results, interpret given results to determine the unknown concentration. So that is our focus today. So it's going to be titration, a standard solution, and also dilution. It's what we are going to focus on. Right, so let's start with titration, learners, and I believe in your respective schools, your teachers will be able to do a titration experiment with you either this year or next year, because these acids and bases, they also continue to grade 12, or they progress to grade 12. So whatever we are doing this year is going to be the same thing even next year. Right, so when it comes to titration, so what you need to know, titration is a common laboratory technique used in chemistry to determine the concentration of the unknown water solution. So for example, if you're having a reaction or an acid-base reaction, which is acid and a base, right? So if you know concentration maybe of an acid, you can determine the concentration of a base through titration, right? So it involves the gradual addition of a solution of known concentration, which is the titrant, to a measured volume of an unknown solution until the reaction between the two solutions is complete, right? So, and there will be a point where the indicator will change color, right? And then that point, we call it what? The end point. And then the point where the acid has completely reacted with the base, we call it what? The equivalence point. So that is titration. So basically, when it comes to titration, so that is an experimental method that you can use to determine what the concentration of an unknown what solution when it comes to acid-base what reaction, right? So these are the apparatus that we need to perform titration experiment. One, we need burette. So this is burette. Okay, so we need burette, and burette actually it measures what? The volume, right? We also need a conical flask, so, which is also known as an Erlenmeyer flask. So we need a burette, we need a conical flask, we need a measuring cylinder. So this is a measuring cylinder, right? We need a resort stand, right, with a clamp. So this is a resort stand, and then you can see here there is what there's a clamp there. So it's another thing that we need, or another apparatus that we need. Then we also need what? Pipette. So we can choose to use pipette or to use a measuring what? Cylinder. So between the two, right? So both of them actually they measure what? The volume of water of a solution. All right. So these are the apparatus that we need, and when it comes to exams, you will be asked actually sometimes to give the names of those apparatus, so you should know them, right? So this is burette, this is a conical flask or an Erlenmeyer flask, right? We have a measuring cylinder there, you have a resort stand with a clamp there, right? We have a pipette, so we can either use pipette or measuring cylinder to measure the volume of what of a solution. So these are important actually apparatus that we need to perform titration experiment or titration. But basically titration, we perform titration actually to get or to determine the concentration of what of an unknown a solution, right? Then these are the steps for titration experiment. So when you perform this experiment with your teachers in your respective schools, these are the steps that you'll be following. One, you need to prepare a standard solution. So we'll go through that. How do you prepare a standard solution? But you cannot just titrate without starting by preparing a standard solution. So you need to start by preparing a standard solution. And the next two slides, actually talk to how we can prepare or how do we prepare a standard solution. Right, place a known volume of an unknown solution in a conical flask, right? So, and this is called the analyte, right? Add 2 to 3 drops of appropriate indicator or suitable indicator to the solution. And then the titrant addition. So the titrant is added from a burette to the unknown solution gradually while continuously mixing. Then endpoint, stop the titrant when the indicator changes changes color, right? So what is happening here? First thing that you need to do when you are doing titration experiment 1, you will have maybe 2 solutions, right? So it's a solution of an acid and the solution maybe of a base. For example, I'm having maybe hydrochloric acid plus sodium hydroxide. So we know very well what will be produced here. It will be sodium chloride plus plus water, right? So you have those 2 solutions. So this is an aqueous solution. This one is also an aqueous solution. Aqueous solution, and then this one is a liquid, right? So I believe that this reaction is balanced. So let's say you want to determine the concentration of hydrochloric acid. Ne? So you have hydrochloric acid. So you don't know the concentration of hydrochloric acid. You know the concentration of sodium hydroxide solution. So let's say the concentration of sodium hydroxide solution maybe 0.05 mole per cubic decimeter, right? So you know the concentration of sodium hydroxide, but you don't know the concentration of hydrochloric acid. So how can we get the concentration of hydrochloric acid experimentally? So you can use titration to get that, okay? So the concentration of sodium hydroxide is known. So sodium hydroxide actually is going to be our standard solution. So what do we do when we perform this experiment? So remember, you have burette and you also have the conical flask there where you are going to transfer your solutions, okay? So in your burette, you are going to have sodium hydroxide, right? You have your standard solution there. So you know the concentration here, right? So you know the concentration, and then here you are going to have an unknown solution, or maybe hydrochloric acid with an unknown concentration. Okay, so you have your sodium hydroxide, right? In your burette, we know the concentration of sodium hydroxide. So when it comes to your burette is where you are going to transfer your standard solution. And then in a conical flask or an Erlenmeyer flask, you are going to have your the solution of which we don't know its concentration, right? So it's an Erlenmeyer flask here, right? So you will know the volume in the Erlenmeyer flask. So let's say the volume here, it's maybe 30 cubic decimeter, right? But you don't know the concentration here, right? But for the standard solution, which is in the burette, we know the concentration, 0.015 mole per cubic decimeter, okay? And then what we know here, it's the volume of hydrochloric acid. We don't know the concentration, is what we want to find out, right? Then we know the concentration of sodium hydroxide, right? And then what is it that we don't know for sodium hydroxide? Is actually the volume of sodium hydroxide that will be needed to neutralize 30 cubic decimeters of hydrochloric acid. Okay, so then before we start with our titration process, we have to add actually a suitable indicator, right? So there are 3 indicators that we use, right? So for a reaction of a strong acid and a strong base, right, we use to determine the endpoint, we use bromothymol blue, right? But for a reaction of a strong acid and a weak base, we use methyl orange. And for a reaction of a strong base with a weak acid, we use phenolphthalein. All right. So when it comes to this reaction, it's a reaction of a strong acid and a strong base, right? So to determine the endpoint here, the suitable indicator will be bromothymol blue. So we will add few drops of bromothymol blue into that Erlenmeyer flask. All right. So few drops of bromothymol blue, right? Why are we adding bromothymol blue? To actually determine what the endpoint, where an acid has completely reacted with what? With a base, or a base has completely reacted with what? With an acid, right? Then in the burette we have what? The titrant. Okay, and then we have what in our conical flask or Erlenmeyer flask, we are having what? An analyte. Right. So this is how we perform actually this experiment. Ne? So you want to find the concentration of what? Of hydrochloric acid, right? You know the concentration of sodium hydroxide. So sodium hydroxide is going to be our standard solution. Why are we saying it's the standard solution? It's because we know its concentration. All right. So we want to find the concentration of what? Of hydrochloric acid. So in your burette, you are going to have what? A standard solution. In an Erlenmeyer flask, you are going to have your what? Your solution, of which its concentration is unknown. We don't know its what? Concentration. Then you start with the process. You open the tap there. There's a tap here, drop by drop, right? And then you observe the color change, right? So don't just open it as if you're opening what? The normal tap, right? But here you open it drop by drop, so that you'll be able to determine what exactly the endpoint, where the indicator changes what? Color, right? So you drop by drop, you swill or you mix, right? And observe if there is color change. If there is no color change, then you continue until the color changes, all right? So where the color changes, that is going to be your what? Your endpoint, all right? And you have to stop titrating, okay? So when you stop, now what are you going to do? Get the volume of the standard solution that neutralized 30 cubic decimeters of hydrochloric acid. Let's say when you read on your burette, right, you have maybe 25 cubic decimeters. So 25 cubic decimeters neutralized what are 30 cubic decimeters of hydrochloric acid. Okay, then how are you going to get now the concentration of hydrochloric acid? Okay, so the concentration of hydrochloric acid, one of the equations that you can use Ca Va equals to Na over what? Nb. So it's Ca Va over Cb Vb, right? So it's Ca Va over Cb Vb equals to Na over what? Over Nb, right? So Ca, that is concentration of an acid, and then Va, that is the volume of an acid, right? And then Cb, concentration of a base, and then Vb is volume of a base. Then Na is number of moles of an acid from the balanced equation, NB is number of moles of a base from what? From the balanced what? Equation. So do we have concentration of an acid? Our acid here is hydrochloric acid, right? So our acid, we don't know its concentration, so it will be what? Ca. What is the volume of hydrochloric acid here? The volume is what? Is 30 over concentration of a base. So our base, remember, is our standard solution, so we know the concentration of that solution. We said it's 0.05, so it's 0.05. Volume of standard solution, right? Neutralized 30 cubic centimeters of hydrochloric acid. This we got what? The 25 equals to Na. Coefficient of an acid is 1. Coefficient of a base is also what? 1. So it's 1 over what here? Over 1. All right. So then I'm having what? 30 Ca, right? Equals to 0.05 times what? 25, right? Divide by 30, divide by what? 30. So I'm having 0.05 times 25 divide by what? 30. Okay, so what am I having there? I'm having concentration of what now? Of an acid, which is 0.04 what mole per cubic what? Decimeter. So this is how we can get concentration of what? Of an acid. But we got that through this experiment. Okay, so these are the important, you know, apparatus that we need to perform titration, right? The important one here is that burette. All right, so burette is going to give us the volume, right? That what titrated the volume of a solution of which we don't know its what concentration. All right, so then from there, another thing which is important here is the choice of the indicator. Please make sure that you choose a suitable what? Indicator. So you can't use what? Methyl orange, right? If you are having a reaction of hydrochloric acid and sodium hydroxide. Hydrochloric acid is a strong acid. Sodium hydroxide is a strong base. So a suitable indicator cannot be methyl orange. So if you are not going to, you know, use methyl orange won't be able actually to assist us to identify what the endpoint here. So a suitable indicator to determine the endpoint here, where an acid has completely reacted with a base, right? It's going to be what? Promethymol what? Promethymol blue. But another thing which is very, very important, in our burette you have a titrant, right? So in our burette always we will have a solution of which we know its concentration, which is the standard what? Solution. And then in an Erlenmeyer flask you will have the solution of the unknown what? Concentration, right? But the only thing that you don't know is the concentration, right? But you know the volume, right? Of what? Of that solution. Then you start with your titration, but before you start, please don't forget to add few drops of what? The indicator, or a suitable what? Indicator, for you to be able to determine what? The end point. Then from there, when the color has changed, all right? And you need also to know the color changes. The color of promethymol blue in an acid, the color of promethymol blue in a base. So you should know those colors, but you need to observe the color change. So where the color changes, that is the end point. And make sure that you open the tap drop by drop so that you don't miss the end point. So for accurate results or reliable results, you cannot just perform this experiment once. All right, at least have 3 trials and then take the average. Okay, then from there you'll be able to get, you know, reliable what? Results. So you repeat for the first time, second time, third time. So maybe trial 1, trial 2, trial 3, right? Maybe for trial 1 you'll get 25, for trial 2 maybe you'll get 26 cubic decimeters, and then maybe for trial what? 3 maybe you get 24.5 cubic watt decimeters. Then you add the 25 plus 26 plus 24.5, and then you divide that by 3. Then you take what? The average. And when you take the average, yeah, you'll be able to get, you know, at least reliable what? Results. But you cannot just do this once, right? So at least have 3 trials. But basically, when it comes to titration, what are we trying to do here? We are trying to find concentration of of a solution, right? Through what this experiment, right? So I've shown you what the steps that we need to follow when we are performing this experiment, right? Then when it comes to titration, so there's no way that you will titrate without starting by preparing what a standard solution, right? So when it comes to a standard solution, if they say define a standard solution, what is a standard solution? A standard solution, it's a solution of which its concentration is known, or it's a solution of known what concentration. For example, in the previous slide, I gave you concentration of sodium hydroxide is 0.05, right? So we know the concentration of sodium hydroxide, which means that sodium hydroxide is our standard what solution. All right, so a standard solution, it's a solution of known what concentration. So how do we prepare a standard what solution, right? We have talked about titration. How do you perform titration? So I've shown you, right? So when it comes to standard solution, how do you prepare a standard solution? How do you prepare a solution with the known what concentration? For example, you want to prepare a solution, right? Maybe of sodium hydroxide with a concentration of 0.5 mole per cubic decimeter. You want to prepare a solution of sodium what? Hydroxide with a concentration of 0.5 mole per cubic what? Decimeter, right? So we are having sodium hydroxide pellets. It's a solid, right? Sodium hydroxide what pellets, but you want to prepare a solution now of sodium hydroxide, and you want the concentration of that solution to be 0.5 mole per cubic decimeter. Where do we start, right? Apparatus that we need, important apparatus that we need to prepare what a standard what solution. One, it's your mass scale, all right? You need a mass scale, or we can say it's a meter scale, so to measure the mass, right? You also need what a volumetric flask. This is what we call a volumetric flask, right? Okay, what else are you having here? We are having a funnel, right? So we are having what? A funnel. This part, you see this thing? This is what? A funnel. Okay, for you to be able to transfer all the contents into the volumetric flask, right? And then what else do we need? Except the funnel, the volumetric flask. Oh, we also need distilled water, right? So we need distilled water. So this is a squeeze bottle which contains what? Distilled what? Water. All right. Yeah. So these are the important apparatus that you need. Okay. So now we want to prepare a standard solution of sodium hydroxide with a concentration of 0.5. Where do we start? We have to start by, so let's say you have, so this is also another thing that we need. In most cases, we use a wash glass name. Okay, right. So we want to prepare a solution of sodium hydroxide with a concentration of 0.5. Using which volumetric flask? There are different volumetric flasks that we have, or volumetric flask, they have different volumes, right? We have 250 cubic centimeters, we have 500 cubic centimeters, you also have maybe 1000 cubic what centimeters. So let's say this one, it's a 1000. This one, it's a 1000 cubic centimeters volumetric flask, the volume of it. So from this point to this point, the volume is 1000 cubic what centimeters, right? Okay, so now you have two things here, right? You have a volumetric flask, right, of which we know its volume, it's 1000 cubic centimeters, right? You also have the concentration of what? Of the solution, which is 0.5 mole per cubic decimeter. You also have sodium hydroxide pellets, for example, right? So actually we're having sodium hydroxide, which is in a form of a solid here, right? So first thing that you need to do is to get the mass of sodium hydroxide needed to prepare a solution of sodium hydroxide with a concentration of 0.5. How do we get that? The equation, you can use C equals to what? Mass over molar mass times what? Times volume. You are looking for what? The mass of sodium hydroxide needed to prepare a what? 0.5 mole per cubic decimeter a sodium hydroxide what? Solution, right? So concentration is 0.5, right? The mass is what we need. Molar mass of sodium what? Of sodium hydroxide. Sodium, the molar mass of sodium is 23, and then the molar mass of O, it's which is oxygen, is 16, and then for H is what? It's 1. So you have 23 plus 16 plus 1, right? So 23 plus 16 plus what? Plus 1. So I'm having what here? 40. So it will be 40 grams per mole times the volume. The volume is the volume of the volumetric flask. It's not volumetric, volumetric flux that we are going to use. Ne? So we are going to use the 1001. So 1000 converted to what? To cubic decimeters is going to be what? 1. Then the mass needed will be 40 times 0.5, right? So we need what? 20 grams. So we need 20 grams of sodium hydroxide what? Pellets for us to be able to prepare a solution of sodium hydroxide with a concentration of 0.5. So we need 20 grams of sodium pellets, right? Then from there, you measure that 20 grams, all right, using a mass scale. And then after getting that 20 grams, all right, what do you do? One of the things that you can do, you can have maybe a glass beaker. You transfer that 20 grams of sodium hydroxide into that glass beaker, and then you add distilled water. You stir, right? And then until all the contents of or until all sodium hydroxide is what? Is dissolved. Okay. Or another thing that you can do, you can just transfer that 20 grams of sodium hydroxide into a volumetric flask using a funnel, right? And then from there you add distilled water, right? To maybe maybe half mark, right? Then after doing that, you swill, right? Swill until all the sodium hydroxide is dissolved, right? It's another thing that you can do. But where do you start? You want to prepare a solution of sodium hydroxide with a concentration of 0.5, using which volumetric flask? The volumetric flask with a volume of 1000 cubic centimeters, all right? Then first thing that you need to do, you have to start by calculating the mass of sodium hydroxide pellets needed to prepare that 0.5 mole per cubic decimeter. So you've done that. Here we want 20 grams. Then from there, you measure 20 grams of sodium hydroxide pellets. Ne? Then from there, you transfer sodium hydroxide into a volumetric flask. You add distilled water, right? Or have fill the volumetric flask which contains the sodium hydroxide. You swill until all the contents of sodium hydroxide are dissolved. Then from there, you fill the volumetric flask into that 0 mark here. So if you fill it to that mark, already we are having what? A volume of 1000 cubic centimeters. You already know what now? The concentration of this solution is 0.5 mole per cubic decimeter. So it's simple like that. This is how we have to prepare what? A standard solution. You need a volumetric flask, you need a mass scale, you need what? A funnel for you to be able to transfer the solutions, or transfer, those particles of what? Of sodium hydroxide, for example, right? Then from there, you will have what? A standard what? Solution. Okay, so you can see here they have filled what? the volumetric flask, right? Then swill from there. You don't shake. You swill until all the contents are dissolved. After all the contents of sodium hydroxide are dissolved, then is when now you are going to fill to that mark. Fill the volumetric flask to that mark. Already we are having 1000 cubic centimeters of the solution, and then from there you also know the concentration of what? Of that solution. So it's simple like that. That is how actually we need to prepare what? A standard what? Solution. Standard solution. Don't forget the apparatus that we need to prepare what? A standard solution. But what is a standard solution? A standard solution is a solution of known what? Concentration. How do we prepare that? These are the steps that we need to follow for us to be able to prepare what? A standard what? Solution. Then after preparing a standard solution, then you can move to titration. So for you to titrate, you have to start by preparing what? A standard what? Solution. And then from standard solution, what do you do with that standard solution? You transfer that standard solution into a burette, right? So you fill the burette to a 0 mark, all right? Then from there, you have a standard solution in your burette, all right? So you already know the concentration, all right? And then from there, on your conical flask or Elmer flask, you have a solution of which you don't know its what? Concentration, but you know its what? Volume, all right? Then from there, before you start titrating, right? You have a titrant on your burette, you have an analyte on your what? On your Elmer flask, right? But before you start titrating, you need to add few drops of a suitable what? Indicator. So I've already talked about the suitable indicators. You need to look at your reaction, right? Your neutralization what? Reaction. It's a reaction of what? A strong acid versus a strong base. Okay, then I have to use bromothymol blue. A reaction of what? Of a strong acid and a weak base, I have to use methyl orange as an indicator. Reaction of a strong base and what? And a weak acid, so I have to use phenolphthalein for what? To determine what? The end point. All right, so that is how you have to do it. Then after adding those few drops, you can start titrating, right? You open the tap drop by drop, right? So don't just open it because it's possible that you'll miss actually the end point. So drop by drop, one drop, you observe color change, or you mix and then check if there's color change. If there's no color change, then you continue until the point where the color will change, right? And then from there, at that point, you should know that is what the end point, which is what we call the point where the indicator changes color. It's where an acid has completely reacted with a base, or a base has completely reacted with what? With an acid. Then from there, you read from your burette the volume of standard solution that titrated, the known volume of what? Of a solution of which its concentration we don't know, right? Then from there, you do your calculations, and then from there, you will be able to get what? The concentration of the other what? Solution. So we use titration to get the concentration of the unknown what? Solution, right? Then there is also what we call dilution. So we are still going to look at the calculations, or the stoichiometric calculations based on what? Titration, and also what? Standard what? Solution. But for now, let's look at dilution, okay? So when you talk of dilution, learners, dilution, when you dilute, remember we have concentrated solution and the dilute what? Solution, right? For example, we have concentrated acid, concentrated base, dilute acid, dilute what? Base. What is concentrated acid or concentrated base, right? Concentrated acid contains large amount of an acid or large amount of a base in proportion to what? To the volume of water. That is concentrated acid or concentrated base, right? Dilute acid, dilute base contains small amount of an acid or a base in proportion to what? To the volume of what? Of water. In proportion to the volume of what? Of water. So when it comes to dilution, if you want to dilute a solution, you add water. You cannot dilute a solution of hydrochloric acid with sodium hydroxide, right? So you dilute using water. So water is the solvent. Actually, when it comes to dilution, what is important here, we dilute using what? Water, right? So you can't say when you add hydrochloric acid solution to sodium hydroxide solution, then you have diluted what the two solutions. No, when it comes to dilution, you add water. Okay, so when you add water to a concentrated solution, what happens? The solution becomes dilute. So you dilute a solution using what? Water. That is very, very important. Right. So you dilute a solution using what? Water. Then, another thing when it comes to dilution, which is very, very important. When it comes to dilution, remember we're saying you add water to a concentrated what solution. Then after adding water to a concentrated solution, the solution becomes dilute. Right? Then the concentration of the solution will change. That is the first thing. The concentration of the solution will change. Right? Remember, if initially the solution is concentrated, we are expecting its concentration to be greater than 1. Right? Then after addition of water, remember we are diluting the solution. Right? We are expecting the concentration of that solution to be less than 1 to show that now the solution is what? Is dilute. Okay? Right. So concentration changes. Right? From maybe above 1 to below 1 when you add water. All right? Then another thing which is very, very important here, learners, when it comes to dilution. Remember, we dilute a solution with water. Right? So you can't say I'm diluting sodium hydroxide with sodium hydroxide or hydrochloric acid with hydrochloric acid. You dilute using what? Using water. Right. Then another thing which is very, very important when it comes to dilution. Please note this, learners. The number of moles does not change. The number of moles does not change. What changes is the concentration and the volume. Right? But the number of moles does not change during dilution. The number of moles of that acid or the number of moles of that base does not change during what? Dilution. What changes is the concentration. What changes is the volume, not the number of moles. So the number of moles before dilution, the number of moles of that solution before dilution will be equal to the number of moles of that solution after what? Dilution, after adding water. So number of moles does not change during what? Dilution. What changes is the concentration. Solution changes from being concentrated to dilute after adding water. Concentration changes from being above 1 to being below what? 1 during what? Dilution. But the number of moles does not change. So the number of moles before dilution will be equal to the number of moles after what? Dilution. Then the equation that we can use to perform calculations when it comes to dilution is this equation. C1 V1 equals to C2 V2. Where is this equation coming from? We are saying when it comes to dilution, the number of moles, right, before addition of water, which is the initial, right, will be equals to what? The number of moles after addition of water, right? So the number of moles before dilution will be equal to the number of moles after what? Dilution. And how do we calculate the number of moles? From the equation C equals to N over V, right? Your N will be CV. Even this one will be what? CV. Hence here we'll say maybe initial, final. But we prefer to use what? C1 V1 equals to what? C2 V2. So this will be before dilution, and then this will be what? After what? Dilution. So this is the equation that we use when it comes to what? Dilution. So please be careful. Be able to determine that this is dilution, right? So don't think adding HCl to HCl, that is dilution. Sodium hydroxide to sodium hydroxide, that is dilution. Oxalic acid solution to oxalic acid, that is dilution. No. Dilution, we add what? We add water. So when we add water, please note that the number of moles remains the same. So the initial number of moles will be equal to the final number of moles, or the number of moles before dilution will be equal to the number of moles afterward dilution. Hence, we have C1 V1 equals to C2 V2. Right. Okay, so when it comes to C1V1 equals to C2V2, so C1 that will be the concentration of the solution before addition of water, which is before dilution. What is V1? That is the volume of the solution to be diluted. So this is before addition of what? Of water again, right? C2, that is the concentration after addition of water. And that concentration, we are expecting that concentration to be less than 1 actually, okay? After addition of what? Of water, okay? Then volume of the dilute solution, that is V2, right? So this is the equation that we can use to perform calculations under what? Dilution. But dilution, we dilute a solution with what? With water. And if we dilute a solution, it moves from being concentrated to dilute, all right? But what remains the same when it comes to that solution is the number of moles before dilution and after what? Dilution. Concentration will change, volume will change. So what doesn't change is the number of moles. How does concentration change? It changes from being, the solution changes from being concentrated to dilute. So the concentration will change from being above 1 to being below what? 1. What will happen to the volume? The volume will increase because we are going to add water, right? We are going to add water to what? To the solution. To dilute that solution, we add water. So we are expecting the volume of the dilute solution to be higher than the volume of what? Of the solution before dilution, right? Calculations on dilution. Let's look at the first one. What are they looking for? Calculate the volume of 2 mole per cubic decimeter sulfuric acid needed to prepare 1000 cubic centimeters of 0.5 mole per cubic decimeter sulfuric what? Acid. So sulfuric acid is concentrated initially, right? Then water was added. After addition of water, the total volume of the solution now is what? Is 1000 cubic what? Decimeters. And what is the concentration of that solution after addition of water? Now it's what? It's 0.5. You can see now the solution of sulfuric acid is now dilute. I'm looking at that number is less than what? Or that concentration is less than 1. Okay, so what are they looking for? They are looking for what? The volume, the initial what? Volume. So the volume of the solution before addition of water, or the volume of the solution before what? Dilution. All right. So one of the equations that we can use, we are saying it's what? C1 V1 equals to C2 V2, right? So concentration before dilution is 2. We are looking for what? Volume before dilution. What is the concentration after addition of water, after dilution? They're saying it's what? It's 100. Okay? So if it's 100, remember that 100 is in cubic what? Centimeters, which means that V1 will also be in cubic decimeters when it comes to our final answer, right? But if you want our V1 to be in cubic decimeters, right, which is the SI unit for volume, we need to change that volume in cubic centimeters to cubic decimeters, dividing by what? By 1000, which is going to be what? 0.1. So we have the concentration, which is 0.5, the volume, which is what? 100. Ne? Then V1 will be 0.5 times 100 divided by what? Divide by 2. Okay? Then what will be V1? 0.5 times 100, it's 50, divide that by 2, which is what? 25. So here we are having 25 what? Cubic what? Centimeters, which is the same as what? 25 times 10 to the power negative 3 cubic decimeters, or 0.025 cubic what? Decimeters. So this is the volume, the initial volume before what? Dilution. Okay? Or what we can do, we know that when it comes to dilution, number of moles remains the same. All right? So what you can do, you can calculate the number of moles after dilution. Okay? So number of moles after dilution will be CV, right? Concentration after dilution, 0.5, times volume after dilution, it's what? But now you need to be careful. You need to change. You don't have a choice here. You need to change that V in cubic centimeters to cubic what? Decimeters, which is going to be what? 0.1. So it's 100 divided by what? 1000. So what is 0.5 times 0.1? 0.5 times 0.1, it's 0.05 what? Mole. So these are number of moles after dilution. But we know that number of moles during when it comes to dilution remains the same. Okay? So now I can calculate what so this was C2 V2. Now this is C1 V1. What was the concentration initial? Is 2. And then the volume, initial volume, it's what we are looking for. And then number of moles remains the same, which means that here is 0.05. Ne? So I'm having divide by 2 here, divide by 2. So what is 0.05 divide by 2? I'm having what? V1 as 0.025 cubic what? Decimeters. So you can see we are getting same answers here. All right. So that is dilution, learners. We dilute a solution, right, using water. During dilution, concentration will change, volume will change, but number of moles remains the same before and afterward dilution. Number 2, calculate the concentration of a 20 cubic centimeters solution of sodium hydroxide needed to prepare 250 cubic decimeters of 0.38 mole per cubic decimeter of sodium what? Hydroxide. Now we are looking for what? Concentration. The initial, actually concentration of what? Is it the concentration of concentrated sodium hydroxide or the concentration of dilute sodium hydroxide? It should be the initial what? Concentration, which is the concentration of concentrated sodium what? Hydroxide. So calculate the concentration of a 20 cubic centimeters solution of sodium hydroxide needed to prepare 250 cubic centimeters of 0.38 mole per cubic decimeter sodium what? Hydroxide. So we have a volume after dilution. We also have what? The concentration after dilution. We don't have the concentration before dilution, but we have the volume before what? Dilution. So now let's calculate the concentration before dilution. So concentration of sodium hydroxide. Ne? So it's going to be what? C1 V1 equals to C2 V2, right? Concentration is what we're looking for. What was the volume? 20, right? So let me double check. It's 20. Yes, it is 20. So 20 equals to C2. The concentration they said is 0.38. And then the volume is what? Is 250. Okay? Volume will be 250. Remember, this is in cubic centimeters. This is also in cubic what? Centimeters. So there's no need for us to convert here. So cubic centimeters will cancel out cubic what? Centimeters. Right. So divide by what here? 20. Divide here by what? By 20. So C1 will be 0.38 times 250 equals to divide by 20. So what are we getting here? 4.75 mole per cubic what? Decimeter. And you can see this concentration, it's for concentrated solution. You can see the concentration is above 1, right? So it's what we were looking for. Or start by calculating the number of moles. So number of moles will be C2 V2. C2 is 0.38. V2 is 250 cubic centimeters. So convert cubic centimeters to cubic decimeters, divide by 1000. So divide 250 by what? By 1000. It's going to be what? 0.25. Ne? So I'm having 0.38 times 0.25, which is going to be what? 0.095 what? Mole. Number of moles remains the same before and after what? Dilution. So N equals to C1 V1. N will be 0.0 0.95 equals to, we are looking for the concentration before dilution times what? What was the concentration before volume before dilution is 20, which is going to be what? 0.02. So it's going to be what? C1 will be 0.095 divided by 0.02, which is going to be what? 4.75 mole per cubic what? Decimeter. So we are getting the same answer. All right, I hope we are still together here, learners. It's dilution, we dilute using water. Then if they can ask you the volume of water that was added to a concentrated solution of sodium hydroxide, or I think this time is sodium hydroxide. The volume of water that was added, initially you had 20, then final solution you're having what? 250, right? So we'll just say 250 minus what? 20, which is going to be what? The volume of water that was added here, it was what? 230 cubic decimeters of what? Of H2O, to make a solution of what? Of 250. So we added what? 230 cubic centimeters of water to that 20 cubic centimeters of the solution of sodium hydroxide to get a dilute solution of sodium hydroxide with a volume of what? Of 250 cubic what? Centimeters. Right. Okay. Now let's move to the third question. Let's move to the third question. Right. Right, so third question, calculate concentration of dilute solution of hydrochloric acid prepared from adding 120 cubic decimeters of water to 150 cubic decimeters of hydrochloric acid solution with a concentration of 1.28 mole per cubic decimeter. Right, so we want the concentration of the dilute solution. Actually here we're looking for C2, all right? So it's going to be what? C1 V1 equals to C2 V2. Right. We are looking for the initial concentration here is what? For the concentrated solution of hydrochloric acid, it's 1.28. Initial volume. Let's read and understand the statement. What was the initial volume? So they're saying here, calculate the concentration of dilute solution of hydrochloric acid prepared from adding what? 120 cubic decimeters of water to 150 cubic decimeters of what? Of hydrochloric acid. In other words, what are they trying to say here is that here initially we had what? 150. Here we had what? 150 cubic decimeters of hydrochloric what? Acid, right? And then that is initially. Then final, we added what again here? We added 120. Then what will be the total? It's going to be what? What is this? 0017, sorry, 270. So I'm having what here? 270 cubic what? Decimeters. Okay. So the initial volume, it's 150. We are looking for the concentration of the dilute solution. Final volume is 270. Not 120, not 150. So the total volume, it is the volume of the initial solution plus the volume of water that was added. So they added 120 to 150. So the total will be the volume of the dilute what? Solution, or the final what? Solution, which is going to be what? 120 plus 150, which is going to be what? 270. Right. So I hope you understand where this 270 is coming from. The initial, it was 150 cubic decimeters of solution of hydrochloric acid. Then it was diluted by adding 120 cubic decimeters of what? Of water. So the final solution, which is the dilute solution of hydrochloric acid, will have a volume of 120 plus 150, which is going to be what? 270 cubic what? Decimeters. Right, then your C2 here will be 1.28 times 150 divided by what? 270, right? So it's going to be what? 1.28 times 150 is 192, divide that by what? 270. So I'm getting 0. What? 0.71 mole per cubic what? Decimeter. And I was expecting concentration that is less than 1 here. Why less than 1? Because now the solution is dilute. I've added water, so the solution has moved from being concentrated to dilute. So I'm expecting the volume, sorry, the concentration to be what? Less than 1. So you can see it's less than 1 is 0.71 mole per cubic what? Decimeter. So that is dilution basically. Yes, what is important here, concentration changes, volume changes, but the number of moles before dilution equals to the number of moles after what? Dilution. C1 V1 equals to C2 V2. Where is that C1 V1, C2 V2 coming from? From N equals to CV. Number of moles remain the same. Okay. Right, so let's look at calculations based on standard solution. Standard solution is a solution of which its concentration is known. Then how do you prepare? We have talked about that, how we prepare. It's very easy to prepare a standard solution. You know the apparatus that are needed to prepare a standard solution. Right. Then let's look at the questions related to standard what solution. 1. Standard solution of sodium hydroxide is prepared by dissolving 224 grams of sodium hydroxide pellets into a 250 cubic centimeters of water. Okay, so that is how they've prepared a standard what solution. Okay, so they've prepared a standard solution of sodium hydroxide by dissolving 2.24 grams of sodium hydroxide pellets into a 250 cubic centimeters of water. First question that they want us to do is to calculate the number of moles of sodium hydroxide. There are equations that we can use to calculate the number of moles, right? And they are there on our data sheet, right? You can use N equals to mass over molar mass. You can use N equals to CV from the equation C equals to N over V, okay? You can use V over Vm. You can use N over Na. But here, we are given what? We are given the mass of sodium hydroxide. Then we can get the molar mass from the periodic what table. The molar mass of sodium hydroxide from the periodic what table. So let's calculate the number of moles. So number of moles, I'm using mass over molar mass. Why mass over molar mass? Because I'm given the mass and I'm also given the substance, and I can get the molar mass of that substance using the relative atomic masses from what? From the periodic table. So the mass is 2.24. No need to convert, because when it comes to this equation, we want mass in grams, not mass in kilograms. If mass was given in kilograms, then we're going to convert those kilograms to what? To grams, right? But already mass is in grams here, so there's no need for us to convert that. Then the molar mass. Molar mass is not from heaven, but from the periodic table. What is the relative atomic mass of sodium hydroxide? So we are looking for what? Sodium what? Hydroxide. What is the molar mass of sodium hydroxide? Relative atomic mass of sodium from the periodic table is 23. Relative atomic mass of oxygen is 16. The relative atomic mass of hydrogen is what? It's 1. So here I'm having 40 grams per what? Per mole. I'm having 40 grams per what? Per mole. Okay? Right. So I'm having 40 there. Then the number of moles will be 2.24 divided by what? By 40. All right? So which is what? 0.05 what? 6 what? Mole. So these are what are number of moles, okay, of sodium what? Hydroxide. Then that is our question 1A. Second question, concentration of sodium hydroxide what? Solution. Okay, concentration, there are two equations from the data sheet, right? There are two equations that we can use to calculate what? The concentration. Okay, concentration is C equals to N over V, and C equals to mass over molar mass times volume, right? So I can use C equals to N over V. Why C equals to N over V? Already I'm having the number of moles. The number of moles, 0.056. Okay, 0.056. And the volume, let's check the volume that was used. The volume that was used is 250 cubic centimeters. So cubic centimeters in this equation, we don't want volume in cubic decimeters, right? But C1, V1, C2, V2, it doesn't matter because those units will cancel out, right? But in this one, we don't have a choice. C equals to N over V. That V, even when it comes to C equals to N equals to V over Vm, that V should be in cubic what? Decimeters, unless if Vm is given in what? In cubic centimeters. But when it comes to these equations, V should be in what? In cubic decimeters. So here, our V is in cubic centimeters, so I need to convert those cubic centimeters to cubic decimeters. So I divide that 250 by 1000, then to get what? 0.25. So it's going to be 0.056 divided by what? 0.25, ne? Which is going to be what? 0.224 mole per cubic what? Decimeter. Okay, or you can use C equals to mass over molar mass times volume. The mass is 2.24, molar mass is 40, volume 0.25. Then you should also get 0.224 mole per cubic watt decimeter. So let's check. 2.24, right? Divide that by 40 times 0.25. 40 0.25, ne? So it's 40 times 0.25, so it's 10. So I'm having 2.24 divided by 10, which is the same, yes, 0.224 mole per cubic watt decimeter. So you can either use C equals to N over V or use C equals to mass over molar mass times volume to get the concentration. All right, I hope we are still together, learners. Number 2, a dilute solution of oxalic acid has a concentration of 0.08 mole per cubic. So to me, when I read this statement, it does make sense. It shows, even that concentration, it shows that the oxalic acid solution is dilute. Its concentration is less than 1, right? So it's a dilute solution of oxalic what? Acid. So one of the questions that they can ask here is oxalic acid a strong or a weak what? Acid. You should know that oxalic acid is one of the common weak what? Acid. And that oxalic acid can be dilute. It can also be what? Concentrated. But whether it is concentrated or dilute, that doesn't change its strength. It remains a weak acid. So let's be careful when it comes to that. Be careful, learners, when it comes to that. Your oxalic acid, it's a weak acid, right? Which can also be dilute and what? Concentrated. So being concentrated oxalic acid, it doesn't mean that the oxalic acid now has changed from being weak to what to strong. It's still a weak acid, but it's just that now it's what is concentrated. And how are you going to see that this oxalic acid is concentrated? Look at the concentration. If that concentration is greater than 1, it's a solution of oxalic acid, which is what? Concentrated. But if that concentration is less than 1, for example this one, it means that this oxalic acid is what? Is dilute. Okay, so but oxalic acid is still a weak acid. It can either be dilute, can also be what? Concentrated, but it remains what? A weak what? Acid. And you know what is a weak acid. Those are some of the equations that they can ask, right? You know why it is what a weak acid. A weak acid ionizes incompletely in water to produce or to form low concentration of hydronium what ions. So they can ask you why oxalic acid is a weak acid. It ionizes incompletely in what? In water to form low concentration of hydronium what ions. Is oxalic acid in this case dilute or concentrated? It is dilute. Why am I saying it's dilute? Its concentration is less than 1. That is very, very important. Okay. So here you are given the concentration of this dilute solution of sodium of oxalic acid. All right. And then you are also given the volume, which is 30 cubic decimeters. They want us to calculate the mass needed to prepare this solution of oxalic what? Acid. Okay. So for us to get the mass, we are given the concentration. We are also given what? The volume. Right? So we need the mass. Mass, it is going to be mass equals to number of moles times what? The molar mass. So first thing that we need to do is to get what? The number of moles. Right? How do we get the number of moles given concentration in the volume? N equals to CV, from C equals to N over V. C 0.08, V 0.03. Why 0.03? Where is that 0.03 coming from? Because I see 30 here. That 30 is in cubic centimeters, so I have to convert it to what? To cubic decimeters. Then I will get the number of moles there. 0.08 times 0.03, which is 0.0024. And learners, please be careful. Do not round off these answers. You only round off your final answer, right? Please follow the instructions. When we are writing an exam, you are given instruction, and one of the instructions will say round off your final answers. Not just any answer, but round off your final answers to 2 decimal places. So this is not your final answer. So you're not supposed to round off it. So the answer that we're going to round off to 2 decimal places will be the mass, which is what we are looking for. Right, now we have the number of moles, which is 0.0024. Right, then we need the mass of oxalic acid. You can see here, they are testing you, right, whether you know the chemical formula for oxalic acid. It's one of the things that you need to know. It's a requirement. You need to know it. Know the chemical formula for oxalic acid, right? So oxalic acid is open brackets, COOH, close what brackets, then what? 2. That is the chemical formula for oxalic what? Acid. Then what are we looking for? We are looking for the molar mass of oxalic what? Acid. So molar mass of oxalic acid will be, how many carbon atoms are we having here? Is 2. So it will be 2 times 12. Where is that 12 coming from? From the periodic table. That is the relative atomic mass of carbon, right? So it's going to be what? 24, right? How many oxygen atoms are we having here? There are 4, not 2, because it's open bracket, close brackets, then what? 2. So it's 2 plus 2, which is going to be what? 4. But what is the relative atomic mass of oxygen? From the periodic table is 16. So it will be 16 times 4, which is 64. And then hydrogen, it's 1 times 2, which is 2. So I'm having 64 plus 2, which is 66, then 66 plus 24. 66 plus 24. 66 plus 24, which is what? 90. So I'm having what here? 90 grams per what? Per mole. That is the molar mass of oxalic what? Acid. But if you didn't know the chemical formula of oxalic acid, you are not going to get this question right. Okay? So it's one of the things that you need to know. Know the chemical formula of those common acids and then those common bases. Chemical formulae and also the names. So times 90 here. So 90 times 0.0024. So I'm having what here as the mass? 0.216 grams, or 0.22 if we are round offing it to two decimal places. I'm having what here? 0.22 what grams. That is the mass of oxalic acid needed to prepare 0.08 mole per cubic decimeter solution of oxalic acid with a volume of 30 cubic centimeters. All right, so that is our number 2. Number 3, give one term for a solution of which its concentration is precisely known, or precisely known, right, or exactly known. So the name will be a standard solution. That will be a standard solution. Standard solution is solution of known concentration. So give one term for a solution of which its concentration is precisely known. So that solution, we call it a standard solution. So these were calculations, stoichiometric calculations based on standard solution. Right. Now let's look at titration calculations. Right. So when it comes to titration, remember we talked about titration, and titration is an experimental method that we can use to determine or to get the concentration of a solution. We went through the steps, right? So the only thing that you need to do at your respective schools is to perform that experiment. Same with the standard solution. We went through the steps. So the only thing that you want to do in your respective schools is to prepare that solution, or to do that experiment to prepare a standard solution. Right. Titration. A 25 cubic centimeters solution of sodium hydroxide with a concentration of 0.2 mole per cubic decimeter is titrated with 30 cubic centimeters of hydrochloric solution. So this is titration. This is not dilution. If it was dilution, then it was going to be addition of water, right? Remember, we dilute using so this is titration, which is between acid and and a base. All right, so we are having a reaction of acid and a base here, right, to produce maybe salt and water, because it's a neutralization reaction. Okay, so here I'm having 25 cubic centimeters of sodium hydroxide with a concentration of so the concentration of sodium hydroxide is 0.2. So this sodium hydroxide, one of the questions that they can ask here, sodium hydroxide, is it an acid or a base? You should know it's a base, right? And what is the base? You can define a base according to Arrhenius. You can define a base according to Lorentz-Bronsted. According to Lorentz-Bronsted, what is the base? It's a proton acceptor. According to Arrhenius, it's a substance that produces hydroxide ions in aqueous solution. So those are some of the things that they can ask. Okay, sodium hydroxide, we are saying it's a base, right? So if it is the base, is it a strong or a weak base, right? So in this case, you should know common acids and common bases, or common strong acids, common strong bases, common weak acids, common weak bases. So this is a strong base. Okay, we are saying it's a strong base. Why is it a strong base? It's a strong base because it dissociates completely in water to form high concentration of hydroxide ions. Okay, it's a strong base because it dissociates completely in water to produce high concentration of hydroxide. So please don't confuse hydroxide ions with hydronium ions. So hydronium ions are produced by acids, and then hydroxide ions are produced by bases when they're dissolved in water. But this one is a strong base. Why is it a strong base? Because it dissociates completely in water to form high concentration of hydroxide ions, right? So we are saying it's a strong base, right? And then this strong base, in this case, is it dilute or concentrated? Okay, it is dilute. Why am I saying it's dilute in this case? Because its concentration is less than 1. So those are some of the things that they can ask, okay? And you can see they're not there, they're not part of the questions here, but they can ask that, okay? Right. Then they're saying to us, write down a balanced equation, right? So sodium hydroxide is titrated with what? Hydrochloric what? Acid. What will be produced here? So you're having sodium hydroxide, Na, so ions that are present there is Na plus and OH what? Minus in that aqueous solution of sodium hydroxide. In this aqueous solution of hydrochloric acid, there are hydrogen ions and chloride what? Ions, right? Then there will be ion exchange here. Then this sodium will be attracted to this, what? Sodium ion will be attracted to that chloride ion to form what? Na what? Cl. This hydroxide ion from sodium hydroxide will be attracted to that hydrogen ion from hydrochloric acid to form what? H2O. So it will be sodium hydroxide plus hydrochloric acid to produce sodium chloride plus what? Plus what? And then is the equation balanced? Yes, it is balanced. Sodium atoms 1 this side, even this side 1. Hydrogen atoms 2 this side, even this side is 2. Oxygen atoms is 1, even this side is what? Is 1. So that is the balanced what equation. The ratio of sodium hydroxide to hydrochloric acid, it's 1:1. And actually the ratio here throughout, it's 1:1:1:1. Right. So that is the ratio. We have the balanced equation now. Give the name of a suitable indicator for this titration. So to determine the end point for this titration, right, we have to use which indicator? Right, you need to check the reaction. This reaction is the reaction of a strong base and what? And a strong acid. And the suitable indicator will be what? Bromothiamol blue. It's going to be what? Bromothiamol what? Blue. It's a reaction of a strong acid and a strong base. So the suitable indicator to determine the endpoint here will be bromothiamol what? Blue. Calculate the concentration of hydrochloric what? Acid solution. Right? Because this is a titration. Okay? I prefer to use this method. Right? Start by calculating the number of moles. Number of moles of what? Sodium hydroxide. Why sodium hydroxide? It's because you have the volume and the concentration of sodium what? Hydroxide. It can't be the number of moles of hydrochloric acid. Because for hydrochloric acid, the only thing that we have for now is only the volume. So if you try to use the equation n equals to Cv from C equals to n over V, you are going to have two unknowns. But for sodium hydroxide, there is only one unknown, which is the number of what? Of moles. So what am I doing here? I'm calculating the number of moles of sodium hydroxide, which is going to be Cv. Concentration is what? Let's check the concentration. 0.2. 0.2. Volume 0. What? Yes, 0. What? 0.25. So it's 25 divided by 1000 there. Okay? Then 0.2 times 0.025. So I'm having 0.005 mole. So these are number of moles of what? Of sodium hydroxide. Okay? Then how am I going to get the number of moles of hydrochloric acid? Mole ratio. From the balanced equation, HCl is to what? NaOH. Ratio 1:1. If it's 1:1, therefore, the number of moles of hydrochloric acid is also going to be what? 0.005 what? Mole. Since the ratio is 1:1 from the balanced what? Equation. All right? Then, now I have the number of moles. Remember, we are looking for the concentration of hydrochloric what? Acid. Concentration of hydrochloric acid, we have the number of moles now. C equals to N over what? Over V. N 0.005. Volume that was used to neutralize 25 cubic centimeters of sodium hydroxide, it's what? Is 30. Okay? So here it is going to be what? 0.03. Why is 0.03? I'm converting cubic centimeters to cubic decimeters. So divide this by what? 0.03. Which is going to be what? the concentration will be 0.17 mole per cubic watt decimeter. That is what the concentration of hydrochloric what? Acid. Concentration of hydrochloric what? Acid. And then, because this is a titration, another equation, but this is the method that I prefer to use. With this method, we'll never go wrong. But this one of CAVA over CBVB, we use it if there is complete what? Neutralization. If there is complete what? Neutralization. All right. So for complete neutralization, concentration of an acid, it's what we are looking for. Volume of an acid, it's what? 30. Concentration of a base, 0.2. Volume of a base that was used is what? To completely neutralize that acid solution, it's 25. Number of moles from the balanced equation of an acid, it's 1. Balanced equation of a base is also what? 1. So I'm having concentration of an acid, right, equals to 0.2 times what? 25 over what? Over 30. So the concentration will be what? 0.2 times 25 divided by what? 30. So I'm also having what? 0.17 mole per cubic watt decimeter. But this one, please be careful. Use that equation if there is complete neutralization between acid and what? And a base, right? Between acid and what? And a base. But for this one, it works. But with this one, we'll never go wrong. The first what? Option, or the first method. The second one, please use that equation if there is complete what? Here? Neutralization. If the end point has been reached. So some questions, they will say the end point has not yet been reached. So we are not allowed to use this equation. You will use this equation if there is complete what? Neutralization. Hence, I avoid using it. I'm not saying there's something wrong with it, but when it comes to stoichiometric calculations, I avoid using this equation because I have to use this equation if there is complete what? Neutralization. The end point has been reached. Ne? Okay. Or sometimes they will say the endpoint has been passed, right? So which means that you can't use this what? Equation. So this one, we use it if there is complete what? Neutralization. Complete what? Neutralization. So please be careful. Don't just use it because you see it's a reaction or it's a titration of an acid and a base. Then you just say CAVA over CPVA, VP equals to NA over NB. But please be careful. We use that equation if there's complete neutralization. An acid has completely reacted with a base, and a base has completely reacted with what? With an acid. Okay. Then let's look at the second question. They want us to define the term end point. So end point, that is the point where the indicator changes color. Where bromothermal blue will change color, that is what we call the end point. And at that point, an acid has completely reacted with a base, and a base has completely reacted with what? With an acid. Okay. So that is the end point. Point where the indicator changes color. Point where indicator changes color. That is the end point. So that is the point where the indicator changes what? Color. Let's look at the last what question there, or in our activity 3. Standard solution of sodium carbonate. Standard solution of sodium carbonate is prepared by dissolving 1.33 grams of sodium carbonate powder into 250 cubic centimeters of water, right? 15 cubic centimeters of this solution is then titrated by 22 cubic centimeters of hydrochloric acid solution. Balance equation, this is the balance equation. We have hydrochloric acid plus sodium carbonate to produce sodium chloride plus carbon dioxide plus plus water. Calculate the concentration of hydrochloric acid. Okay? Calculate the concentration of hydrochloric acid. So if you want to calculate the concentration of hydrochloric acid, yeah, we need number of moles of hydrochloric acid. We also need what? The volume of hydrochloric acid. So C equals to N over what? Over V. Okay? So N, we don't have. We have this. C, we don't have. So we don't have this, we don't have this. So you're having how many unknowns here? 2 unknowns. So you have to start by calculating what? The number of moles of what? Of hydrochloric acid. How are we going to get the number of moles of hydrochloric acid? Okay, let's read the statement. So you have a standard solution of sodium carbonate, okay, which is prepared by dissolving what? 1.33 grams of sodium carbonate, carbonate powder into 250 cubic centimeters of what? Of water, right? Then they are saying 15 cubic centimeters of this solution, right? 15 cubic centimeters of this solution is then titrated by what? 22 cubic centimeters of sodium of hydrochloric acid. Okay, so actually this is what is happening here. We are having what? 250 cubic centimeters of what? We are having 250 cubic centimeters of the solution of sodium carbonate, right? So this is what we have. Okay, then we don't know the concentration of this solution. Okay, we have the volume of it, but we don't know the concentration. All right, we also don't know the number of moles here, the initial number of moles here. Okay, then what they've done here, they from this 250, they took only what? 15. But they took 15 cubic centimeters from this 250, right? The concentration here will be equal to concentration here. But for now, we don't know that concentration. Okay? So they are having what here? 250. From this 250, they are only taking what? 15 cubic centimeters. Okay? So first thing that we need to do is to calculate the number of moles of this 15 cubic centimeters. So number of moles equals to what? CV, right? You'll see something. We don't have the concentration of this solution. We only have what? The volume. So my focus for now is sodium carbonate. Okay? So I don't have the concentration of sodium carbonate. I only have the volume, which is 15. That titrated what? 22 cubic centimeters of hydrochloric acid. So first thing that I need to do here is to get the concentration of sodium carbonate. Okay? Why is your number of moles 1? The number of moles for the previous question is 1. Why is it 1? I'm getting 1 from the balanced equation. The coefficient of a base here is 1. The coefficient of an acid here is what? It's 1. Hence, when it comes to Na over Nb, I'm having 1 over 1. Where is this 1 over 1 coming from? From the balanced equation. If I was focusing on this one, this is an acid, this is a base. So Na over Nb was going to be what? Na over Nb here, it was going to be, so I'm trying to answer this question here. Why the number of moles is 1? It was 1 for the reaction of sodium a hydroxide and hydrochloric acid because the ratio of an acid to a base was 1:1. If I was focusing on this one, sodium carbonate and hydrochloric acid, it was going to be what? 2/1. Where is this 2 coming from? From the balanced equation. What is the coefficient of an acid? Is 2. What is the coefficient of a base? Is what? It's 1. Hence, I will have 2 over what? Over 1. I hope it's making sense. But this applies to what? To that equation of Ca Va over Cb Vb equals to Na over Nb. That Na over Nb is the number of moles from the balanced what? Equation. Number of moles of an acid from the balanced equation. Actually, is the ratio. Actually, is the ratio there. That Na over what? Over Nb. When it comes to the equation, Ca Va over Cb Vb equals to Na over Nb. I hope I've answered your question. Right. So first thing that I need here, learners, is the number of what? Of moles. Right? But how am I going to get those number of moles? I have to start by calculating what? The concentration of the standard solution. Let's calculate the concentration of the standard solution. So concentration of standard solution, I can use mass over molar mass times what? Times volume. The mass that was used, it was 1.33. Okay? Over molar mass of sodium carbonate. So sodium is 23. So it's 23 times 2, which is going to be what? 46 plus 12 plus 3 times what? 16. 46 is coming from 2 times 23. So it's 3 times 16 will be what? 3 times 16 will be 48 plus 12 plus 46. So here I'm having what? 106 grams per what? Per mole. That is for sodium carbonate. Sodium carbonate. Okay. Then I'm having 106 here. Volume that was used. Check the volume that was used is 250. Ne? Initial. The initial what? Volume. It's what? It's 250 for sodium carbonate. Ne? So it's 250, which is going to be what? 0.250. Okay? Now I have the concentration. 106 times 0.25. It's 26.5. 1.33 divided by 26.5. Then now I'm having the concentration as 0.05. I'm not going to round off this answer. 0.188,679 mole per cubic watt decimeter. I have the concentration of a sodium carbonate solution. Right? I have the concentration. Then from that 250, they took 15, right? If I'm not mistaken. They took what? 15, yes. So they took 15. Okay. So they took what? 15. So now I'm looking for the number of moles of in that 15 cubic centimeters. Ne? So N equals to what? CV. C is still the same, 0.05, 0.188,679. The volume that was used to neutralize 22 cubic centimeters of hydrochloric acid, it's 15, which is 0.015. Right? So what am I having here is number of moles. I'm having 0.00075,283 mole. So these are number of moles. Okay? Then how am I going to get the number of moles now of hydrochloric acid? Ne? Hydrochloric acid is 2 sodium what? Carbonate. Ratio 2:1. Where am I getting this 2:1 from? I'm getting 2:1 from the balanced what? Equation. The coefficient of HCl is 2. The coefficient of Na2CO3 is what? It's 1. Hence, I'm saying 2 is to what? Is to 1. I'm looking for what? The number of moles of hydrochloric acid, okay, is to the number of moles of what? Of sodium carbonate, which is 0.0007 what? 528 what? 3. Ne? Cross multiplication, which means that actually the number of moles of hydrochloric acid, we multiply these ones by 2 times what? Times 2, which is going to be what? 0.00150,566. These are number of moles of hydrochloric what? Acid. Now we got the number of moles of hydrochloric acid. We can now calculate the concentration. C equals to N over what? Over V, which is 0.00150,566 divided by the volume that was used to neutralize 15 cubic centimeters of sodium carbonate. They used 22, right? So convert that 22 to cubic decimeters, which is going to be what? 0.022. Then we'll get what? The concentration. So divide by 0.022. Then the concentration will be what? 0.07 or 684 mole per cubic watt decimeter. Round off to 2 decimal places, then it should be 0.07 mole per cubic watt decimeter. Right, so here it was a long one, but we were supposed to start by calculating what? The concentration, right? Then concentration, from concentration, calculate what? The number of moles in 15 cubic centimeters. Then from there, after calculating the number of moles in 15 cubic centimeters, this is what we got. Then mole ratio to get the number of moles of hydrochloric acid, multiply the number of moles of sodium carbonate by 2. We got this one. After getting the number of moles of hydrochloric acid, then we calculated what? The concentration of hydrochloric what? Acid, number of moles divided by volume that was used to neutralize 15 cubic centimeters of sodium carbonate. Then we got 0.07 mole per cubic watt decimeter. Then we can also use CAVA over CPVB equals to NA over NP. But first thing that you need to do is to start by calculating what? The concentration. All right? So start by calculating what? The concentration. So if we calculate the concentration, already we have calculated what? The concentration. Okay. So I'll just erase this part and see if we'll get the same answer or what. So this one is the last question. So CAVA, our CA, that is the concentration of an acid, which is what we are looking for. VA, volume of an acid, it was 22. And then concentration of a base, it's what we calculated. This is the concentration of a base. Concentration of a base, 0.050. Yeah, let's use that one, which is this one. So it's 0.050, right? Times the volume of a base that was used, it was 15. Then from the balance equation, number of moles of an acid is 2. Number of moles of a base is what? It's 1. So concentration, like it or not, here will be what? The same as, because it will be 1. So we will have what? CA equals to 2 into 0.050 times what? Times 15 over what? Over 22. Then you should get the same answer. But where should you start? Start by calculating the concentration of the standard solution. Move with that concentration, and then from there, calculate the number of moles in 15 cubic centimeters of that solution using the same concentration. Then get the number of moles of sodium carbonate from number of moles of sodium carbonate, mole ratio, get the number of moles of hydrochloric acid, and then from there get the concentration of hydrochloric acid. So here I'm having 0.050 times 15, right, times 2. This is what we have. Divide by 22. So yes, I'm getting 0.0 mole per cubic decimeter, which is, I think even this side we got the same thing. Yes, 0.07 mole per cubic decimeter. So learners, our focus was on titration. How do you perform titration? Apparatus that are needed for titration. Standard solution. What is the standard solution? How to prepare a standard solution. We went through those steps and the apparatus that we need to prepare a standard solution. Calculations, stoichiometric calculations based on standard solution. You saw that. Dilution, also diluting a solution, you use water, right? And then it was titration, stoichiometric calculation. So I think for today, what we have done, it's enough. Thank you so much for watching this lesson. I hope you gained a lot. Enjoy the rest of this day. See you next week Friday, and then next week Friday we are going to consolidate acids and bases, and then the following week it will be redox reactions. So but for next week we are just focusing on exam type questions, the multiple choice questions, and then from there we'll be done with acids and bases for this term, and then that other week it is going to be redox reactions. Thank you so much, your grade 11s. See you next week. Bye bye.